Hello and welcome! This is a video tutorial on how to use the REMCU lib on a Raspberry Pi embedded computer. Now, we're going to show you how easy it is to expand hardware of a Raspberry Pi board using a $1 STM32 microcontroller and some wires. C++ applications and Python scripts ran on the Raspberry Pi will gain access to internal microcontrollers' peripheral modules like DAC, ADC, GPIO, and others, as if these peripherals were part of the Raspberry chip itself. And we will not even have to develop a microcontroller firmware or kernel drivers for this. Now, to interact with the chip's hardware from the embedded computer, we're going to have to use the driver functions of the standard peripheral library of STMicroelectronics Company. It's a vendor software development kit for writing firmware. You could see detailed information about the standard peripheral library on st.com. There is documentation and samples which are useful for working with STM32. We will call these driver functions from our user space Linux applications just like we called them for hardware operations from firmware code. The REMCU library makes it all possible. How it works is the library translates a local driver function call on an embedded computer to a remote call of the same driver function on the chip using a communication or debug interface. You can see a description of the REMCU lib and other tutorials on the website remotemcu.com. Alright, let us begin. So, first of all, we need a Raspberry Pi board, some wires, a board with the STM32 F103 high-density chip, and an oscilloscope to display analog signals. Beforehand, we prepared a Raspbian image with some examples. Download it from our site and unpack the archive. Write the image to your SD card using the official Raspberry Pi documentation. Insert the card into the board and switch the Raspberry Pi on. Then, you're going to need to connect a keyboard and a monitor, or connect using SSH. By default, the system has a static IP address of 192.168.0.10. The default login is PI, all lowercase, and the default password is Raspberry, and all lowercase letters as well. Home directory has everything necessary to build and run the examples. This image has a community version of the REMCU lib, which works through debug interface and OpenOCD Utility. Connect these Raspberry GPIO pins to the debug port of the microcontroller using this scheme. Now this image has the pre-built OpenOCD application. To easily run it, we prepared this script. Run the openocd.sh scripts and start another SSH session. Navigate to the examples directory and run the make command. As you can see, several applications were now created. The triangle wave app is the slightly modified 2 channels triangle wave sample of standard peripheral library, which generates a triangle signal using DAC and a built-in generator. Alright, let's run the application. Connect the probe to the PA4 pin. The oscilloscope shows a triangular wave. You can specify the signal period and cycles using the startup arguments. Now let's try to change the period. Take a look at it now. The signal frequency has also changed. If you run into some trouble while trying to launch these examples, see the troubleshooting page on our site or issues page on the GitHub repository. Now on to the next part. The second app generates an escalator signal. The DAC module of STM32 doesn't have a generator for producing this wave. but the wave can be created by using both DAC and DMA modules. A DMA enables buffering received and transmitted data from peripherals to the microcontroller's memory. And the REMCU library can load and store the memory from a personal computer. In this way, you can upload signal data to the chip's memory and control DAC using DMA. The code of this application was practically taken right from the one-channel DMA escalator sample of the vendor library. Alright, let's run the app. Now the oscilloscope should be showing an escalator wave. You can specify the signal period and cycles using the startup arguments again. Let's try to change the period. As you can see, the signal frequency has also changed. Before we move on any further, I would like to note that we didn't develop this microcontroller firmware. Our Linux program directly works with DAC, DMA, and RAM modules using a remote procedure execution of the standard peripheral library. The ways you can use the REMCU library are not limited to these DAC, DMA, and RAM blocks. There are other peripherals that are also available. A small application called the ADC Line captures ADC data and builds a horizontal bar chart based on this value. Plug a variable resistor into the PC4 pin and run the application. Now rotate the shaft and you will get the voltage versus time chart. There are also other samples of vendor libraries that can be adapted to run on a Raspberry Pi. One just needs to add several REMCU functions. You can get both their description and documentation on our site. The C and C++ programs we've been using are not the only languages you can use with the REMCU library on a Raspberry Pi board. Alternatively, you can also call the REMCU library using other programming languages. Since Python is an official recommended programming language for the Raspberry Pi, let's see some Python examples. The GPIO.py is a simple script that toggles the PB12 microcontroller pin. The ADC Line.py script builds a horizontal chart of the ADC value versus time like the previous ADC Line application. For your convenience, we prepared a special Python wrapper containing all necessary constants and structures that enable you to use the driver function just like with the C and C++ code. The REMCU lib provides not only the API for a standard peripheral library for working with an STM chip, it can also be implemented with other interfaces like HAL, Mbed, Arduino, and others. Furthermore, there are versions of REMCU for other chips, including 8-bit, 16-bit, 32-bit microcontrollers, and 64-bit systems on a chip. This library can be ported to any version of the Raspberry Pi board, as well as much less or more powerful embedded platform. Thank you very much for your attention. Now, if you have any questions on these examples, please just raise an issue in our GitHub repository or send us an email about your questions on the REMCU lib.